In the previous lecture, we discussed that the Reynolds transport theorem, by considering extensive properties like mass and linear momentum, only tells us about the overall behavior of the fluid. However, it does not give us the detailed information about the fluid motion. Okay, that's why we need some differential equations instead of integral equations to understand the detailed information of the fluid flow. And that's why we considered an infinitesimal control volume and used Reynolds transport theorem by considering extensive property as mass to get the continuity equation, which was del rho by del t plus divergence rho v equal to 0, right? This was called the continuity equation. This is known as the continuity equation. Okay, so now let's apply a similar analysis, similar approach to get equations by considering the extensive property as linear momentum. So let's again consider a cube with edge length dx, dz and dy. Okay, next let's say we again want to derive for the case when we don't know whether the flow is steady or unsteady, whether it is uniform or non-uniform, and whether the fluid is compressible or non-compressible. So we want to derive for a general system. Okay, we want to derive the equation by considering nxt, the extensive system property, as linear momentum, considering that the flow can be steady or unsteady, uniform or non-uniform, and compressible or non-compressible. Okay, so since this is a next new part, let's just draw a line like this. Since it's a new part, it has nothing to do with continuity equation. Okay, all right, so now let's again consider the surfaces which have their normal vector parallel or anti-parallel to x-axis. Okay, so the surfaces that I have just marked are the surfaces that have normal vector perpendicular, normal vector parallel or anti-parallel to the x-axis. So this has its normal vector, so the area vector in this direction, and it has its area vector in this direction. Okay, now just like in the case of when we considered extensive property as mass, we derived for only two surfaces, and then similarly we said that we can derive for other surfaces, and we wrote down the equation. So here also we'll do the similar thing. Okay, so let's first write the Reynolds transport theorem. So the expression is this: d by dt integral over control volume plus integral over control surface eta vxyz dot dA equal to dN by dt. Okay, and this was for the system. Okay, now in our case, since we are considering extensive property as linear momentum, so what will be eta? Eta will be the property divided by mass, and in this case the property is linear momentum. Linear momentum is nothing but mass times velocity, so mass gets cancelled out with mass and we will be left with velocity. Okay, so this is v x y z vector. Alright, so let's put eta here. So this will become d by dt v x y z rho dv over control volume cv plus control surface v x y z. Oh sorry, I forgot rho here. So rho v x y z dot dA equal to dn by dt, and dn by dt is dp by dt. And what is the rate of change of linear momentum? It is nothing but the summation of all the external forces. Okay, now just like we did for the previous case, let's consider this as 1, let's consider this as 2, and let's define this as, let's define this surface as CS1, let's define this as CS2, and others has CS2, the others has CS3. So since this is 4x, I should say, if I follow the sequence, this will be CS3, this will be CS4, and the back portion of this is CS5, and the front side, which is this one, okay, will be CS6. I'm not writing it, but keep in mind that that is CS6. And let's just remove the CS5 also, so that the image looks clean. Okay, so let's focus on CS1 and CS2. Okay, so now what will be 2,1? 2,1 will be this term for the control surface 1, correct? So that will be integral over, let me just write it with different color. So this will be integral over CS1 vxyz rho vxyz dot dA. Okay, and since at CS1 my x is x minus dx by 2, so I can write that these terms should be for x minus dx by 2. Okay, or should have a fixed x minus dx by 2. Now recall that vxyz was u I hat plus v j hat plus w k hat, and rho is a function of x, y, z and t, and this we defined at the center x, y, z. Okay, now on the control surface, let me draw with some other color. So let's say this is our control surface, the elemental area of the control surface. Okay, and this was our cube. Okay, so this was the elemental area of the control surface, and dA vector points like this, and v vector we have considered ui hat plus vj hat plus wk hat. So v vector at xyz is, let's say, like this, some vxyz, and we want a, here we want a dot product of vxyz with dA vector. So what will be that? That will be the component of this vxyz along x-axis. So this was our x-axis. What will be that? That will be u, correct? And since they are opposite to each other, vxyz dot dA will give us minus u dA. Okay, all right. So for this, the term will become vxyz rho u dA, and with vxyz and rho and u have, so vxyz rho and u are defined with a fixed x, which is x minus dx by 2. Okay, and this is integrated over CS1. Now again we can argue that for a function f of x integrated over x1 to x2 dx with x2 minus x1 very very small, this will become f of x delta x, right? So similarly here also we can write this term as vxyz rho u dy dz, because the area is in the yz plane. Okay, and with these values at x minus dx by 2. Since the dot product gave us negative, I should write there should be a negative here also. Now we can use Taylor's series, which states that f of x plus delta x is equal to f of x plus f prime x delta x plus some higher order terms which can be neglected. So let's just write that f of x plus delta x is nearly this, and f of x minus delta x is nearly f of x minus f prime x delta x. So this will become v xyz at x, which was vxyz minus the derivative with respect to x, so it will be del v xyz by del x and delta x. What was delta x? Delta x is dx by 2. Okay, similarly we can write for rho and we can write for u. So let's just write it down. So rho at x minus dx by 2 can be written as rho minus del by del x rho dx by 2, and u becomes u minus del u by del x dot dx by 2. Okay, so the multiplication, let's do the multiplication. So minus sign will be outside, so let's multiply vxyz with, okay, so let's first multiply these terms. So let this be outside. Let's multiply this with this, so this gives you rho u minus rho del u by del x dx by 2 minus del rho by del x dx by 2 times u plus del rho by del x dx by 2 del u by del x dx by 2, and this can be neglected since del rho by del x and del u by del x, these variations will be smaller as compared to these variations, so we can neglect this term. So this will become like this. Okay, now let's multiply these terms. So this will become negative sign outside. So let's multiply vxyz first. So this will be vxyz rho u minus vxyz rho del u by del x dx by 2 minus vxyz del rho by del x dx by 2 u. Now let's multiply this term. So this will be minus rho u del vxyz by del x plus rho del vxyz by del x del u by del x dx by 2. So now let's multiply this with this. This will give you del vxyz by del x del rho by del x dx by 2 u. Again we have del v by del x del rho by del x, so we can neglect this term can be approximated to be equal to 0, so let's not write this term, and we'll be left with this expression. Okay, so there will be a dx by 2 also here. Okay, so this is the integral over cs1. Now integral over CS2 will be written like this. So to save your time, what I have done is I have just copy pasted the whole all the equations that I got from 2-1, and so this was for 2-1, and the red point, the red color denotes for 2-2. Okay, so wherever the correction would have been for CS2, I have used the red pen. So let's say this was actually x minus dx by 2, but now for CS2 x is actually x plus dx by 2, and similarly I have changed the signs everywhere for CS2. Okay, so if you follow that, you will get this equation 2-2, but my 2-1 was this thing, and then what will be integration over CS1 plus integration over CS2? That will be simply 2-1 plus 2-2. Okay, so now let's see if on addition, which terms remain and which terms get cancelled out. So since there is a negative sign out, okay, since there is a negative sign out, on addition the only terms which will get cancelled out will be the ones with the same sign. So this and this will get cancelled out, because if you take positive inside, this will be positive. If you take negative inside, this will become negative. So then on addition, so let's just write it with some other color so that you can follow it after. So this is 2-1, this is 2-2. So on addition, this term and this term will get cancelled out. These have different signs, so they won't cancel out, they won't cancel out also, they won't cancel out also, and these terms have same sign, so they will get cancelled out, and we'll be left with, let's just write it quickly. So we will be left with, so adding this to this will give you 2 vxyz rho del u by del x dx by 2. This 2 gets cancelled out with this 2, this 2 gets cancelled out with this 2, so I can just remove 2 from here. Now let's add this term and this term. What will this give me? So this will give me plus 2 vxyz. Now note here there will be vectors. Okay, this is still a vector equation. So 2 vxyz del rho by del x dx by 2 u, and again I can remove 2 from here and 2 from here. Now similarly adding this and this will give me rho u del by del x vxyz dx by and dx. Okay, and okay, so dx, now I can take, since dx is common in all the 3 terms, I can take dx outside. So this times dx. Okay, now can you recognize how can we write this term in a more compact way? So can I write this as del by del x vxyz rho u? So using chain rule, you can see that this can be written in a more compact way like this. Okay, so and dx is also there. Okay, there should be, I have done a mistake here, so there should be dy dz also. So this dy dz I forgot to take outside, so let's just quickly write them out. So this is dy dz, dy dz, and there will be dy dz here, and there would be dy dz multiplied from here, multiplied here. So we will get dy dz outside and dy dz here. Okay, so this was simply the sum of two control integral over two control surfaces. Okay, so similarly, if you do integral cs3 plus integral cs4, that will give me del by del y vxyz rho, not u but v, because v is a component of vxyz along y-axis, and this will be dy dx dz. And similarly cs5 plus cs6 will give me del by del z vxyz rho z, not z but w, the component of vxyz along z-axis, dz dx dy. Okay, so adding these three will give me 2. Okay, now let's focus on one, which was, so one was integral del by del t rho v. Again I have used Leibniz rule to take dy dt inside of this integral, and this is over dv. Okay, and again using that dx dy dz are very small, so I can remove this integral and I can write this directly as dx dy dz. Okay, so now what will be summation over f external? That will be 1 plus 2. So this becomes, so what is 1? 1 is del by del t rho vxyz dx dy dz plus del by del x v xyz rho u dx dy dz plus del by del y vxyz rho u rho v dx dy dz plus del by del z vxyz rho w dx dy dz. Now since dx dy dz is common in all the terms, I can just take it outside. Okay, now to further solve this expression, we can use earlier derived continuity equation. So from continuity equation, what we know? We know from the continuity equation that del rho by del t plus divergence over rho v equal to 0. So we would like to break these terms in such a way that we get del rho by del t and divergence over rho v. Okay, so how can we break this term to get del rho by del t? We can simply differentiate. So we can just use chain rule to get this as rho del v by del t plus v del rho by del t. Okay, so let's first break this term. So summation over f external is equal to del rho by del t vxyz plus rho del by del t vxyz plus, now see, we want divergence over rho v, rho and v. So let's consider vxyz rho as one quantity and u as u or v or w as other quantity, and integrate in this way and differentiate in this way. So differentiating in this way can give us, this will give us u del by del x vxyz rho plus vxyz rho del u by del x. Similarly I will get del by del y vxyz rho plus vxyz rho del v by del x plus w del by del z vxyz rho plus vxyz rho del w by del z. Okay, so now what I have here is vxyz del rho by del t, but here I have del rho by del t. So in order to write the continuity equation, I should have vxyz del rho by del t plus vxyz divergence rho vxyz equal to 0. I have some terms like this. If I have two terms like this, I can equate it to 0. Okay, so I have one of the terms which is vxyz del rho by del t, but I don't have, if you see from here, currently I don't have this term vxyz divergence over rho vxyz. Okay, so I think the best way is actually to open all the terms. I think that would be the most easy thing. So let's open. Okay, so this term will remain as it is, del by del t vxyz. Let's open this term. This will be plus u vxyz del rho by del x plus u rho del by del x vxyz plus vxyz rho del u by del x plus v, what is this term? This is rho del vxy z by del y plus v vxyz del rho by del y plus, what is this term? This cannot be simplified further, so this will remain as it is. What will be this term? This will be w rho del vxyz by del z plus w v xyz del rho by del z plus this term which is v xyz rho del w by del z. Okay, so now let's try to see how can we get this term. So let's just first open this term so that it becomes more easy for us to see. So this term is vxyz divergence over rho vxyz. Okay, all right. So what will be this? This will be divergence is I hat del by del x plus j hat del by del y plus k hat del by del z times rho v vector is u I hat plus vj hat plus wk hat. Now if I multiply I hat with I hat, what I will get? I will get I hat with I hat, j hat with j hat and k hat with k hat. I will get del by del x rho u plus del by del y rho v plus del by del z rho w. So I have to get terms, I have to club all the terms which contain vxyz outside and del by del x rho times the component magnitude del by del of that axis times rho times the component of velocity along that axis. Okay, so what are those? Let's see, do we have those terms or not? So what I want is, so this term I already have in the continuity equation. Let's just mark it with some other color. So this I already have. Now we want vxyz outside. So this term has vxyz outside. So let's just first mark all the terms with vxyz outside. So this has vxyz outside, this has vxyz outside, then this has vxyz outside, this also has vxyz outside, this also has vxyz outside, and this also has vxyz outside. This will be del w by del z. Okay, So let's just write them. So what we have here is v xyz del rho by del t. For convenience, let's just mark it again like this so that you can follow it easily, that this term is this term. Okay, now let's write this term, which is u v xyz del rho by del x plus v xyz. Now since in all these terms v xyz is outside, let's, for our convenience, let's write v xyz outside. So now this term has u del rho by del x plus this term has rho del u by del x. Okay, now similarly I have this term v xyz is outside, which is this, and then we have v del rho by del y plus rho del v. Actually this will be y del v by del y. Let me just check what I have done wrong. This will be del v by del y. Okay, because this is del by del y is sitting over here and will act on rho and v. Okay, so just correct this. This is del by del y and this will be del by del y here also. Okay, alright, so this will be del v by del y, rho del v by del y. Okay, plus w del rho by del z plus rho del w by del z. So we have written all the terms which I marked like this. Okay, alright, then we'll just write the remainder of the terms, which are, let's again for convenience mark them like this. Okay, so then this will be euro. Okay, this will be euro del by del x v xyz plus v rho. I can see that rho is common in all the terms. Let's just write it like this: del by del y v xyz plus w del by del z v xyz. Okay, alright, so now let's just first copy paste this term again for the next line. Let's just copy paste it here. Okay, and now let's do the simplifications in this equation itself. Okay, so now this is v xyz del rho by del t and this is v xyz times these terms. So can you see a compact form of, let's say, u del rho by del x plus rho del u by del x? That is nothing but del by del x. Okay, let me just write it with black: del by del x of rho u. Okay, and similarly I can write this equation as del by del y of rho v. Similarly I can write this as del by del z rho w. Okay, alright, now can you see this equation? So this is the same equation which I write here. Okay, so there is v xyz del by del x rho u plus so on. So we can write this as v xyz outside and del rho by del t plus divergence over rho v plus, so this I have written, plus I can't see del v over del t here, so have I missed it somewhere? Yeah, so I have, so there is my rho del v over del t which I missed, so there would be plus rho del v over del t also. Okay, So this will become rho del by del t vxyz plus u del by del x plus v del by del y plus w del by del z on the xyz vector. Okay, now from continued equation I know this term will be 0, so I'll be left with this term, which is rho del v by del t plus u del by del x plus v del by del y plus w del by del z times vxyz. So if I take vxyz outside, this was actually rho was multiplied on these terms also, so I have put a bracket here now. So if I take vxyz outside, this can be written like this. Okay, now can you recognize this term? This is our expression for the material derivative, right? So if you remember, we can write d by dt of some quantity as del by del t of that quantity plus v dot divergence of that quantity. Okay, now in this case my quantity is vxyz vector. Okay, alright, so now we can write this as rho d by dt of vxyz. So this is equal to summation over all the external forces. Okay, so this is the expression that I get by considering infinitesimal control volume and using Reynolds transport theorem by considering the extensive property as linear momentum. Okay, please note that this derivation is still not complete because we have to still define the external forces. For that, infinitesimal control volume. So we'll take let's say the force due to shear stresses, the force due to normal stresses, and the body force, and we'll expand this equation in terms of the by writing down the external forces from the known shear stress and normal stresses. Okay, but before that, before going in that direction, let's first focus on this expression. Oh, I forgot dx dy dz term also. So the summation of rev external was 1 plus 2, and there was a dx dy dz term also. Okay, so we wrote it outside but forgot to put it, and we added all the terms together. So let's just write it as summation of external dx dy dz, then this will be consistent, and at the end there should be a dx dy and dz equal to summation of x. Okay, alright, so it may look to you that dy dt is acting on vxyz and also dx dy dz. That's actually not the case, so let's just write it outside dx dy dz and dy dt v xyz. Okay, now let's see this from a different point of view. So let's say we in some fixed xyz we had a probe. Okay, so let's say we have set a probe at a fixed xyz, and from that probe we want to find what is the total force at a fixed xyz in time t measured by this probe. So what will be that? Now from Eulerian approach we know that the summation over f external measured, let's just write it in a better way. So let's assume that a probe is fixed at x, y, z, and the force measured by the probe at x, y, z at time t is the total force, which is summation over f external. So from Eulerian approach we know that this will be m times dv by dt. Okay, and from Eulerian approach we know that this dv by dt can be written as this. Okay, and let's say at that point the mass is rho times, so let's say the probe, so let's say this is our probe and this is the volume element with volume dx, dy, dz. So I can write this as rho dx, dy, dz. Okay, and in Lagrangian approach this is nothing but dv by dt rho dx, dy, dz, dv by dt, and this dv by dt is also written as this. Okay, to show that this is in the Lagrangian approach. Now you can see that this equation and this equation, this is summation over f external, and this equation are identical. So this means that Reynolds transport theorem for infinitesimal control volume is same as Eulerian approach at a point. Okay, and if you think it carefully, then what's happening is we started with RTT for a finite control volume. Okay, and for infinitesimal what we have done is we have taken it infinitesimal, which is like this, and this is also what we do with the Eulerian approach, because in the Eulerian approach we have a point, and since we are working with a continuum hypothesis, there should be a volume element about which we are measuring the system properties. Okay, so in most of the books you can see that the derivation for the linear momentum for infinitesimal volumes they start from here, because physically RTD for infinitesimal CV is actually the Eulerian approach at a point, and that's why we can write this directly, rho dx dy dz times the material derivative of vxyz. Okay, alright, so if this is clear to you, let me put a question. So the question is as follows. So we know that RTT for differential or infinitesimal volumes is same as Eulerian approach at xyz. Okay, so can you derive continuity equation by considering Eulerian approach? So let's see, can we derive it or not? And intentionally I'm going to do one mistake which you people think about, and the correction to that mistake I'll put that in the description box. Okay, so let's start. So I can use dm by dt equal to 0 because the conservation of mass tells me that I can neither create mass and nor destroy it unless I am in relativistic regime. Okay, so if d by dt of m is 0, then using the concept of Eulerian Lagrangian to Eulerian approach, I can write this material derivative d by dt m, which can also be written like this, and in the Eulerian approach this can be written like this: del by del t plus v dot divergence m. Okay, alright, and since this dm by dt is equal to 0, this has to be equal to 0. Okay, alright, so now I can write m as rho times dx dy dz. Okay, so then the equation would become del by del t plus v dot del rho dx dy dz equal to 0. Okay, so let's take this inside. So this will become del by del t rho dx dy dz plus v dot del rho dx dy dz equal to 0. Okay, now I can write this as del rho by del t dx dy dz del rho by del t plus rho del by del t dx dy dz plus v dot del rho dx dy dz equal to 0. Now this third term I can expand it to give, so I can write v dot divergence as v dot grad of rho dx dy dz, which will become v dot grad rho dx dy dz plus rho grad dx dy dz. Okay, all right, so let's just write these terms: dx dy dz del rho by del t plus rho del by del t dx dy dz plus, now let's write this in terms of these. So this will be v grad rho, or vector is on grad rho dx dy dz plus rho grad dx dy dz equal to 0. Okay, all right, now if dx dy dz is the control volume, not, so we are not thinking about the Reynolds transfer theorem here. So let's say this is the volume of the elemental volume. Okay, so if this is the elemental volume, I will have del by del t of this dv equal to 0 and grad of this dv equal to 0, because it is not going to change. Okay, it will be a constant. So this thing implies I can take this term, I can take this term and this term as 0. Okay, so then this will become dx dy dz del rho by del t plus v grad rho. Okay, so there is a dot product, okay, equal to 0. So this I can also write as v dot grad rho equal to 0 into, so this is also multiplied by dx dy dz. Okay, so if I take dx dy dz common, I'll be left with del rho by del t plus v dot del rho equal to 0. But my continuity equation is del rho by del t plus divergence of v rho equal to 0. So if you want to open this, this will be del rho by del t plus v grad rho plus rho divergence v, and this term I can write as divergence of, I can write this as v dot grad vector on rho. Okay, I think okay, so let me just write this again. So this will be rho divergence v plus v grad rho. Okay, equal to 0. So now if you compare this equation with this equation, I have one term missing in this equation, which is this term. Okay, so what's the mistake I have done in the whole derivation? by considering Lagrangian to Eulerian approach that you people think about. Okay, the solution. So there is a mistake, so let me just write it. I have done an intentional mistake and you figure out that mistake. Okay, and I have given the solution to that mistake in the description box. Alright, so there is something wrong with this equation. Okay, so you people figure that out. Alright, I can give you one clue that all these properties are correct. So I have not done mistake in the mathematics, there is some mistake in the physics part. Okay, and the clue is I have done some mistake while considering the properties about this elemental volume. Okay, so just think about that, think about the physics and not the maths. This all mathematics is correct. Okay, so the properties like divergence over phi a vector equal to phi divergence a plus grad phi. How does we write it? So this is plus a dot grad phi. These all are correct, there is no mistake in this. Just think about the physics. Okay, alright, so let me just repeat briefly what we did so far. So we, by considering Reynolds transport theorem for infinite small volume, we derived summation f external, and with the extensive property as linear momentum, we derived summation f external as rho dx dy dz times dv by dt, which we could also identify as the material derivative. So we can also write this as dv by dt. From this we got an understanding about the relationship between the Reynolds transport theorem and the Eulerian approach. Okay, and so that you can appreciate the concept of Reynolds transport theorem more, I gave you a problem to derive continuity equation using Eulerian approach. So intentionally I did a mistake while deriving the continuity equation from the Eulerian approach, and I could reach till here. So del rho by del t plus v dot grad rho equal to 0, and we can identify that this is a wrong equation, and the correct equation for the continuity is del rho by del t plus divergence rho v equal to 0. Okay, alright, so the solution to this is given in the description box. Alright, so in the next lecture what we'll do is we will derive the most popular equation in fluid mechanics, known as, so in the next lecture we'll derive the most popular equation in fluid mechanics known as the Navier-Stokes equations. Okay, this will do by considering or by writing the external forces in terms of the force due to shear stress, the force due to normal stress, and also the body forces. Okay, this is actually written as this. Alright, thank you for taking this lecture.